Right. So transformers. What we're going to look at is basic operation of a transformer, which is pretty much standard stuff you'll probably all have covered before anyway. I'm going to talk about the assumptions that we're making when we talk about what's called the ideal transformer, because what we're going to be doing over the next week of 3 or 4 weeks, or teaching weeks, is developing a model of a real transformer, so we can look at how what losses there are involved in a real transformer. So in order to do that, we need to know what assumptions we're assuming if we say the transformer is ideal, i.e. if it's 100% efficient. We're going to have a look at what's called impedance ratio, which is an important topic for what we're going to do, analysing transformers, so that we can use what's called the reflected impedance, or transfer impedances over to one side of the transformer, and more about that later. And then we'll look at solving some problems with the reflected impedance method. All right, so that's the plan for this evening. So, transformers. AC circuits commonly connected together using transformers. Coupling is done magnetically rather than directly a direct electrical connection. Allows, for example, a high voltage low current circuit to be connected to a low voltage high current circuit. Their efficiency is normally very high, greater than 98%, leading to minimal energy losses. There isn't a convenient equivalent to a transformer for a DC voltage, and the use of transformers is the reason that we universally use AC for our power transmission and provision. So they play a major role in electrical power distribution and relatively easily allow for efficient power distribution through high voltage transmission. And the simple equation is that if we put the voltage up for a given load, the power and the current will come down, or the power loss will come down and the current will come down. Okay? So, moving on from that, basics of a transformer. If we start with a coil and we pass AC current through, the result of that is that we get a magnetic field. As we pass our AC current up, down and up, we get a magnetic field that in this half cycle charges up in one direction and then decays away as it falls to zero, charges in the other direction and decays away as it falls to zero again. So we've got a constantly changing magnetic field created around the coil. Yeah. So the poles go from north to south, south to north, and so on. Yeah, all okay with that?
Is that coming from my computer?
No, that's a warning on my iPad that I'm using. So sorry, but I did turn notifications to do not disturb, but they still keep coming up for some reason.
That's fine. I was just worried that it was mine.
No.
Yeah, I think do not disturb only works if you have the screen locked, I think.
Okay. Yeah. Right. Basics of a transformer. Yeah. So if we place a second coil nearby to our first coil, like we got down here, the change in magnetic field from what we'll call a primary coil, or the input side, we put AC in here, this field is expanding and collapsing in this coil, and that this coil is also experiencing that expanding and collapsing magnetic field, the secondary coil. Therefore, as these magnetic lines of force in the second coil cut across the wire, they induce a voltage across this secondary, yeah, V2, and that will follow V1. Yeah. Now, simple method like that with an air gap is not very efficient because we're losing a lot of flux to other areas. So a real transformer would have its windings wound upon an iron core to strengthen the magnetic field and to keep the magnetic field as far as possible within touch of the coils. Yeah. So we put a primary voltage Vp here, and we get a secondary voltage Vs there. Okay. And the current in the primary coil winding generates a flux F in the core here, this green line. In turn, that flux in the core induces a current in the secondary winding. But this core is usually ferromagnetic, so it's good at holding a magnetic flux compared with the surrounding air, so that all the flux flows through the core. So this flux would much rather live within that iron core than it would in air. So it has the effect of keeping the flux all in one place, and you're losing not very much at all. Okay. That symbol down the bottom is the symbol for a double wound iron core transformer. All right. Any questions so far?
No.
Nope.
Good. Next page. Right. So, ideal transformer equation. Now, you will have seen, most of you will have seen the ideal transformer equation before, but this is how and why it is what it is. So from Faraday's law of electromagnetic induction, the induced voltage in the primary coil is equal to N1 times d phi by dt. That Greek symbol there, phi, is the magnetic flux. So that expression there, d phi by dt, is the rate of change of flux. You multiply that by the number of turns to get your voltage. Equally, the induced voltage in the secondary coil is the number of turns on that coil times the rate of change of flux. Yeah, for an ideal transformer, they're equal. Yeah. The fluxes are equal on both sides. Okay. So the magnetic flux common to both coils, hence we can say that V1 over N1 is equal to V2 over N2. And then that can be arranged to say that the ratio of voltages, V1 over V2, is equal to the ratio of the turns, N1 over N2. Yeah. So the ratio of the primary and secondary voltages is equal to the ratio of the primary and secondary turns. Everybody follow that so far?
Yee.
Yeah. Lewis?
Yep.
Ben? Yeah. So, furthermore, an ideal transformer is 100% efficient. So the apparent power is also preserved on both windings. So S1 in VA must equal S2 in VA for an ideal transformer. So if you buy a 10 VA transformer, yeah, then both windings are rated for 10 VA. In other words, what that means is if you've got 10 volts on your primary, that's 1 amp. If you step that up to 100 volts on your secondary, yeah, how many amps would that be? To get 100 VA, that'd be 0.1 amps. Do you see what I mean? 0.1 times 100 is 10, 1 times 10 is 10. So if you step up voltage, you must step down current and vice versa. Okay? So that's where this bit comes in. If S1 and S2 are equal, then I1 times V1, which is S1, must equal I2 times V2. So then you could rearrange that to say the ratio of the voltages, V1 over V2, is equal to the inverse of the ratio of currents. So V1 over V2 is equal to I2 over I1. And the full ideal transformer equation is N1 over N2 is equal to V1 over V2 is equal to I2 over I1. You should try and remember that the current one is always the opposite way up to the other two. Yeah. The other thing I would say is, for convenience, if you had a problem and you're going to use these two ratios to find how many turns you want on the secondary coil, if you're given the two voltages, and then you can start off by writing the thing the other way up, turn them both up the other way is equally true. Yeah.
So would you not be able to flip
Do you
the current?
understand what I'm saying there? If you're working on a problem and you want to find N2, for instance, you can write that, you can invert this one, as long as you invert that one as well. So you can go N2 over N1 is equal to V2 over V1. Everything is still true.
And
But
then
would you
I
not be able to invert the current one as well?
I1 over I2.
Sorry? Yeah,
And then
is equal to I1 over I2. Because
Right.
the current one is always the opposite way up to the other two, Lewis. Yes, you're right.
Yeah.
So what I'm saying is you can choose which way you write them up according to the problem you're trying to solve. Because whichever quantity you're trying to find, you want that on the top, don't you? Make it easier to rearrange.
Yeah.
Yeah? All right?
Yeah.
Just a little tip, that's all. You should still get the same answer even if you start off from the original way. You'll just have more steps in your rearrangement. All right?
Uh-huh.
Everybody happy with that? So that transformer equation is something that I would expect you to remember. All right? Okay, so this ideal transformer equation, what assumptions are we making for that transformer equation to be true? We should just about get this page done before our first meeting time run out. Before undertaking the study of practical commercial transformers, we need to first examine the properties of the so-called ideal transformer. By definition, an ideal transformer has the following properties. It has no losses due to core heating, eddy currents, or the resistance of the windings. Yep. So they assume that the core doesn't heat up. We assume that no eddy currents flow in the core and that the windings have no resistance whatsoever. Its core is infinitely permeable. That means it will accept an unlimited amount of flux without saturating. So you're imagining that's like a piece of conduit that you can put hundreds of thousands of wires in it and that never fills up in terms of magnetic flux. Okay? And thirdly, the coupling between the primary and secondary winding is perfect. So any flux produced by the primary is completely linked by the secondary and vice versa, i.e. there is no leakage flux of any kind. With these assumptions in place, the apparent power supplied to the primary will be equal to the apparent power delivered to the secondary, i.e. it's 100% efficient. All right. So that's what you should have in mind whenever you consider a problem regarding an ideal transformer, just using that equation that we've looked at so far, as that those assumptions would be in place. Yeah. Okay. Any questions?
So when people are designing transformers and whatever, do they always use the ideal transformer calculations, or do they assume losses and stuff?
They would have to take losses into consideration, because there are losses.
Yeah.
And if you, what they do in terms of the other thing you have to take into account for is over the system volt drops and things. So they'll have multiple tap-ins on the transformer, so they can pick a tap-in with slightly different number of turns.
Yeah.
To get the ideal setup when it's in place. So that's kind of more important, really. But they would have to consider what the losses were going to be. Yeah, through both heating of the core, and I mean, I'm not an expert, Lewis. I haven't never designed a transformer, so I don't really know what goes into it. But like anything else, when you get down to that fine detail, there's a lot more to it than when you simplify it.
Yeah.
Yep. Okay. Yeah, you're going to kind of see some of the ideas that might be involved anyway as we go through our developing our model. All right?
Yeah.
Right, I'm going to pause there and set up a second meeting. All right? See you in a minute.